Hi, this is Mr. Huber. In today's lesson, we're going to look at real numbers, and some of their properties and other aspects of them. There are imaginary numbers, which we're not going to deal with at this time. So just think of real numbers as the numbers you're used to seeing, and they're broken down into different categories. We're going to see some of them here. There are whole numbers. Okay, whole numbers, or as you see there, 0, 1, 2, 3, and 4, and it keeps going. There are no mixed numbers, fractions, decimals, no parts of numbers. Okay, so think of, you could order one whole pizza, two whole pizzas, things like that. You wouldn't call up and order 2.5 whole pizzas. Right? And then 0 is also a whole number. I guess you could order 0 whole pizzas, but that wouldn't be very worthwhile. There's also integers, which are all of those whole numbers, and their negatives. So you can see the examples there. It's the same thing going to the negative side. So you have 1, 2, and 3, and then -1, -2, -3, and so on, and including 0 as well. There are also rational numbers. Rational numbers are any numbers that can be written in the form where you can write them as a fraction, a over b, where a and b are both integers. So integers themselves are whole numbers, because you could write 2, for instance, as 2 over 1. That's an integer over another integer. Okay? And you can't have a 0 in the denominator to have a rational number. So it says b cannot be equal to 0. In decimal form, rational numbers do one of two things. They either terminate, that means they end. For instance, 1/4 can be written as 0.25. So if you see the decimal 0.25, that is a rational number because it can be written as a fraction. Or it's a decimal that repeats itself, like 0.3333 forever, which is 1/3 as a fraction. So if you see a decimal that ends at a certain point, or it has a repeating set of digits, then it can be written as a rational number in form of a fraction. Okay? So those are your main categories of real numbers. Okay? We're going to see here in a diagram what that looks like. Okay? The smallest category of real numbers, okay, is the whole numbers. Then you have the integers, and then you have the rational numbers. So if you see over here, right, whole numbers, then you have the larger category of integers, and then you have the larger category yet, rational numbers. So whole numbers are integers and are also rational numbers. Okay, the number 16, for instance, that's a whole number. It's also an integer, and you could write it as 16 over 1, which would make it a rational number. Okay? Then you do have irrational numbers. Those would be numbers that, when turned into a decimal, don't end and don't repeat. The two most common examples would be pi, for instance, as an irrational number, 3.14159, it keeps going, decimal keeps going. And then if you take the square root of any non-perfect square, okay, so for instance, the square root of 9 would be 3 exactly. That's a rational number. It's an integer, it's a whole number. The square root of 2, though, if you put it in your calculators, is a decimal that keeps going forever. So that's an irrational number. These cannot be written as fractions, as an a over a b. So the main irrational numbers you're going to see are either pi or square roots of non-perfect squares. Let's look at the numbers here that we have and see what they would look like on a number line. So we can know how to compare numbers, see where they would fall, again with some fractions, some mixed numbers, some radicals, right? So if we wanted to put these on a number line, okay, so we have our number line here. We'll go 0, 1, 2, 3, 4, and so on, and then we have -1, -2, -3, -4, -5. Okay, so if we look at the first number in our list is 2. That's pretty straightforward, right? We can place the number 2 right here on our number line. Okay. Then the next number on our list, -5, also pretty straightforward. We could put -5 on our number line right there. -1. So these are pretty straightforward. Let's talk about which numbers are greatest and least out of those right now. Okay, the further you go to the left on the number line, the smaller the number is. The further to the right, the larger the number is. So we would know probably that 2 is greater than -1 or -5. Okay? If we talk about -1 and -5, sometimes you think 5. Well, 5 is a bigger number. That must be a larger number. No, -1 is greater than -5. And let's make sure we understand those symbols that we're seeing right there. Okay? So this symbol right here is telling us that this is the greater number. Negative 1 is greater than negative 5. Okay? We could also write that as negative 5 is less than negative 1. Okay, when we do that, we would be able to see here that this symbol is telling us the smaller side here is the negative 5. The larger side is the negative 1. So know how to write these inequality signs when you're comparing your numbers. Okay? If we go back onto our number line now and we look at our next number, 1 4/5. So 1 4/5 would be probably right about there. Okay? We can see where I drew that number. I'll highlight it a little bit. Okay? That is right here. Okay? 1 4/5 is not quite the 2, but it's more than halfway. Right? 4/5 is a little more than half, so it's 1 4/5 right around there. And then if we see negative 4/3, it might be helpful to know that that's the same as negative 1 1/3. Okay? So we go past negative 1 a little bit to negative 1 1/3. Then we'd have the square root of 5. So this is one of those irrational numbers. So when you put in your calculator, it's going to be a decimal that goes on forever. It's going to be a little more than the square root of 4. Okay? So which is 2. So that's going to be a number here. That would be right there, about the square root of 5. Okay? The square root of 5 would be right around that point. We could estimate it. And 1.4 would be here a little bit less than 1 1/2. So it's important to know like 1 4/5, 1.4, where might those fall, which one's bigger or smaller than the other. So we could see that 1 4/5 is greater than 1.4. Okay? 1 4/5 is right here on the number line. 1.4 is right here, right? If 1 1/2 was right here, 0.4 is a little less than a half, 4/5 is more than a half, so we could tell which one's larger or smaller than the other. And we could write that out, know how to write that with an inequality. Okay? Let's look at categorizing these numbers. Okay? So we want to tell whether each number is a whole number, an integer, a rational number, okay, or an irrational number. So let's start with the irrational number. Our irrational number, okay, would be right here. Right? That's an irrational number, because that's going to be a number that we can't write as a fraction a over b. Okay? If we look at which numbers would be whole numbers, okay, the whole numbers would be numbers like 2, and if you look through the list, that's the only one. Okay? Negative 5 and negative 1 are integers. Okay? 2 is also an integer. If you remember, every whole number is also an integer. So the number 2 is whole number. It's an integer. It's a rational number. And it's a real number. So I got a little sloppy there. Then rational and real. We can maybe get that a little more clear there for us. Okay, so rational and real. All right. Every whole number will also be an integer, a rational number, and a real number. Every one. Then if we talk about negative 5, this would be the same for negative 1. It is not a whole number, but it is an integer. It is rational. And it is real. Okay? All the numbers we're going to deal with are real. So that's why in that list it wasn't one of the ones I asked for. Whole number, integer, rational number, irrational number. So I wrote it for the first two, but we can assume they're all real from now on. 1 4/5. Okay? 1 4/5 is not a whole number. It's not an integer, but it is a rational number. Okay, we could write 1 4/5 as a fraction, a over b as 9 over 5. So it is a rational number. It would be a real number as well, but again, we're not going to keep classifying everything as real. Negative 4/3, also a rational number. 1.4, also a rational number. We could write that as a fraction, right? But those are not whole numbers or integers. So we want to understand whole numbers, like think ordering whole pizzas. You wouldn't order negative 5 whole pizzas. okay? But you could order 2 whole pizzas. Integers are anything that doesn't have parts of a number, no fractions or decimals. And then you've got your rational numbers, which is anything that can be written as a fraction. Okay? And really, you can look at it as everything's going to be a rational number unless it's the square root of a non-perfect square, like the square root of 5. That's how you can help identify those. Okay? All right, so moving on here, let's take a quick break. A little ray of sunshine here to brighten your day during this video. Cadillac Mountain is in Maine, and it is the first place in the United States that sees the sunrise each morning because of how far east and up high it is. And that picture you see there is one I actually took from watching a sunrise on Cadillac Mountain this past summer. Beautiful setting, Bar Harbor, a little bit down there along the shoreline, and the sunrise coming up on Cadillac Mountain. In class, asked me I can tell you another interesting fact that I learned about Cadillac Mountain. But pretty nice area and pretty interesting thing there. That is the first place that sees sunrise in the United States. Okay? Let's talk some more about some of the numbers we've been seeing. Okay? We're going to talk about opposites or additive inverses, which can be important like when we're solving equations, right? We want to solve by adding an opposite to cancel things out sometimes. So we want to know that terminology. It's important in math to know the terminology. There's a lot of vocabulary that goes along with things, so we want to know some of this terminology and vocabulary. So 9 and negative 9, that's an example of additive inverses or opposites. They have opposite signs, one positive and one negative. Okay? So negative 9 would be considered the opposite of 9. And if you add opposites, additive inverses, you'll always end up with 0. So keep that in mind. Again, those are things that are important when we're going forward and maybe solving equations using some of that. Okay? Another couple terms to know about some of these real numbers we're dealing with. Absolute value. Okay? The absolute value of a number is the distance it is from 0 on a number line. So if we look at our numbers there, 9 and negative 9 again, if we draw out a number line, right, and we have 0 right here, and if this is 9 and this is negative 9, okay, the distance that we have here is a distance of 9. Okay, the distance we have over here is a distance of 9. They're both a distance of 9 units. Okay, we wouldn't say that you're going negative 9 feet to somewhere. Okay, the distance is always positive. So that's why absolute value is always positive, because how far away a number is from 0. Okay, so the absolute value of 9 will be 9. We can see right over here, the absolute value of 9 is 9. These little bars right here indicate absolute value. When you see that, that indicates you're taking the absolute value of the number. So when you have the absolute value of negative 9, it's also 9, because negative 9 is 9 positive units away from 0. We can see that right over here. Okay? Reciprocals. Reciprocals are sometimes called multiplicative inverses, okay, because we'll see where those are useful in solving equations as well, to cancel out things to get them to be 1. Where we add inverses, get 0, multiply inverses, we get 1. Okay? And the reciprocal is a number of any number, a, would be 1 over that number. Okay, we can see that right down here. A, the reciprocal will be 1 over a. So for example, 5, the reciprocal will be 1 over 5. And if you multiply reciprocals, the product will always be 1. Think product, okay? The word product means multiply. So the product of 5 and negative 5 is always going to be 1. Part of the reason for that, right, we could put this 5 as 5 over 1. And then these 5s would cancel, and we'd have 1 over 1 times 1 over 1, right, will always come out to 1. Anytime you multiply reciprocals, you will get an answer of 1. So let's see a couple examples here. What I'd like you to do is maybe pause the video here, write down what you think the reciprocal of each of these numbers is, and then we'll go over it. Okay, if you've had a chance to try your reciprocals of these two numbers yourself, the reciprocal of 2/3 would be 3 over 2. Again, you don't change the signs or anything. Reciprocal is just take the fraction in this case and flip it over. If you're saying, well, I thought you put it as 1 over the number. Yeah, so if we did 1 over 2/3, that's 1 divided by 2/3, right? That's the same as 1 divided by 2/3. When you're dividing by a fraction, you keep change to multiplication and flip. So 1 times 3 over 2, right? is 3 over 2. You don't need to write out that long process to know that you would just flip that fraction over. So when we talk about the reciprocal of negative 1/7, if it's a negative number, the reciprocal will also be negative, and it would be 7 over 1, which is the same as just negative 7. Okay? And if you think about what's their product, so in this first example, we had 2/3 and 3 over 2. So if I take 2/3 times 3 over 2, again, those will cancel to 1 and 1. The 2's will cancel to 1 and 1. And when you multiply, you're going to end up with 1. The product of reciprocals will always be 1. Okay? So some good properties of these real numbers: know how to categorize them, because you might hear things about whole numbers, integers. You want to know what that actually means. Okay? Know how to work with them. We've seen some examples here where we can work with them in terms of their absolute values, their reciprocals, their additive, multiplicative inverses. So we want to know how to work with those as well as classify them and order them, knowing which numbers are larger and smaller, because sometimes we want to estimate that. And then the one that's kind of a little different with those irrational numbers, right? Square roots of non-perfect squares. So if you can't take the square root of the number and get an exact integer answer, then you have an irrational number, because it would end up being a decimal that goes on forever. Okay? So review those properties, know how to use them, and we'll be working on that in class.